equation, you're graphing the path that this object is moving along. Imagine yourself in an airplane looking down at the ground when you look at this graph. And what you're seeing is this is like a sidewalk, right? Or like the trail that goes around Kearney to Yanny Park and all around out to Cottonville, right? It's there. There might not even be anybody on the path, right? But it's there. That's what this parametric equation is, okay? Then you can imagine an object on the path. And there could be different objects on the path. So you could have different equations, different parametric equations, as we'll see today, that draw the same picture. They have the same path, but they're two different objects, so they have different equations because they're at different places on the path at different times. So Zach, trace on this just trace at 6. And everybody else can be on your parametric equation of Adam Ant here if you want to. That'd probably be a good place to be. And so we trace at 6. And so what that means is that at 6 whatever, minutes, seconds, days, right, and whatever time t is in, at 6 minutes, let's say, Adam Ant is right there on the path, on the trail. Now, I can't even tell just looking at that which way he's going, right? I don't know if he's coming down this way or if he's going up this way or if he's just stopped. But at 6, that's where he's at on the path. And these are his coordinates, 2.3 and 0.7. So at any time, there's both an x position, a horizontal position for Adam, and a vertical position for Adam. And it comes from the two equations. Okay? Now, to Richard's question about this idea of slope and speed. The slope is just the slope of the path. If you were up in the airplane looking down, you wouldn't even have to know an object was on the path to be able to see the slope of the path, right? The slope of the path, we'll get to that in a minute. The slope of the path would just be the slope of this line right here, but it wouldn't have anything to do with that object that's on there. Okay? The speed, however, because there could be two different objects there, both moving at different speeds. Does that make sense? Okay? But they're at the same place on the path. The slope of the path is this for both of those objects. The slope of the path is this, but they have different speeds. Okay? So those are two different things. So that's one way to think about why slope and speed are kind of different. All right? But now we want to get into this whole idea of the x prime and the y prime and the derivative, and y derivative is slope, but it's not speed, and so forth. Okay? So we'll come back to this here in a second. But hopefully that helps a little bit of that. But let's take a look here at a problem that I want to look at. Let's see, this is stuff we did yesterday. Okay, this is problem number 11 from the packet we did the other day, the motion packet. This said that you had a particle moving on the x-axis. Now, so I want everybody to really focus in now and try to see the big, because listen, I could go through, okay, hey, parametric equation, do this, type this in, then you do this, then you do this. But that's not going to do anybody good. We really got to understand what these equations are representing and what they stand for, okay? So in this particular problem, this was the equation you were given for a particle moving horizontally on the x-axis. So I went ahead and I graphed this on my calculator, the way we would normally do a graph like this. This is not parametrics now, right? Forget parametrics for a second, okay? This is just a position function of something moving back and forth on the x-axis. And this is the graph I got, a cubic, which we'd expect. And notice how I labeled the axis. Do you agree with those labelings? T is the input variable, and x is actually the output variable, right? It's kind of strange, but it is the output variable. And so right here at 3, we have an output of 0. Now what's that mean? And not an output is zero. We have a local minimum. We have what is zero? The slope is zero right here, right? Everybody agree with that? The slope of this graph is zero right here. Now what's that tell you about the particle? The particle is stopped. Its velocity is zero. Now since it's going horizontally only, that would be its horizontal velocity. But when we were doing these problems, we didn't really call it the horizontal velocity. We just called it the velocity, right? It was zero. Now, so its velocity and speed were the same, and its slope were the same thing, right? On this graph, the slope is zero, and its speed is zero. I mean, it stopped. So what's the particle doing right through this part of the graph? Okay, increasing, but the particle's moving back and forth on the x-axis, right? Along the floor here. It's moving horizontal. So what's the particle doing right through here? No, this isn't the velocity graph now. This isn't the velocity. This is the position graph. This is x. To the right. Thank you. To the right. His x-coordinate is getting greater. Now over here, here his x-coordinate's negative, right? So he's to the left of the origin, right? He's to the left of zero. And he's getting, so right here he's at the origin, right? And then now he's going farther to the right in the positive side of the x-axis, right? Matter of fact, let's do that in red. That's what I've got this over here for. Let's make this be the x-axis right here. Forget this thing for a minute. Here's an x-axis, right? And just a horizontal axis. And I got a particle that's moving. Now where does he start? Over here? Let's say he starts here at, this would be negative time, we'll say. I don't know what these markings are for sure. Negative time. So noon is like zero, we'll say. Okay, noon is like zero. Every hour, like moving really slow. So this would be like 4 hours before noon. So this would be like 8 a.m., right? So over here at negative 4. He's where? He's get to the left of zero. So he's over here somewhere, right? He's over here somewhere, let's say. And then an hour later, he's at the origin, right? And then, where is he? Farther to the right. And then at negative 1, right, an hour before noon, further to the right. So he's out here, right? And what's happening? He's stopping, right? And now he's coming back to the left. And a little past 1 o'clock, he's back at the origin. And then at 2 o'clock, he's back to the negative side. And at 3 o'clock, he's farther negative, but he's stopped. And then he goes back to the right. Now he's still on the negative side, but he's going to the right, right? Because this graph's going up, right? So that's what this position graph, it's going up and down, but the actual particle's just doing this, right? See, this is the thing we need to be able to visualize here. All right? Now, so on this graph, slope and speed were the same thing. Why? Because our x units up here were like, I don't know what their distance, right? Horizontal distance, like this distance, let's say it's in meters, okay? And then the t-axis is in seconds, right? So when you do slope, you'd be doing dx over dt, right? You'd be doing change in x over change in time. So that would be meters per second. So your slope here would be meters per second. And so the slope is speed, right? So they're the same. And that's why all along this year that's been interchangeable. Okay, everybody good with that? Okay, positive velocity means going right, negative velocity means going left, zero velocity means it stopped. Okay, turning around. All right, now let's dive into parametric equations because it's a real easy leap. Parametric equations give us an equation for its x-coordinate at a time and its y-coordinate at a certain time. So for this particle, this would be the equation of its x-coordinate, where it is on the x-axis at any time. What would this particle's y-coordinate be? Always 0, because he never moves vertically. So couldn't I write this as a parametric equation? Wouldn't that be the parametric equation for this particle? Zach, on your calculator then, let's graph that, and you guys can if you want, or you can just watch, not a big deal. Let's go up here, let's turn that one off. Remember we did that yesterday? Click on that thing over there, and surely there's a keyboard shortcut to turn a graph on and off. Somebody find that for me. Again, I gotta think there's a better way. So you click on that, and then you uncheck that box, because we want to come back to Adam Ant here in a minute. Gotta think there's a faster way. And then on this one, let's put in down here on X2, let's put in that equation we just had up there a minute ago, which was that right there. 1/3 t cubed minus t squared minus 3t. Now, while he's doing that, when I graphed this cubic here, I had to graph it in terms of x, right? I had to put x cubed minus x squared because I was graphing it in function mode, not in parametric mode, right? So if you can really understand the difference between these two situations, right? This is parametric. This is actually modeling. It's like Sydney said earlier. This is modeling the motion. This parametric graph's cool because it actually shows us the path it's on and where it is at certain times on that path. Whereas this graph doesn't really show me that. I mean, it's the y values here is its position, and the inputs are its time that it's there. But it's not a real picture of the motion. So that's why parametrics are kind of cool. All right, so if we go to this, dang it. Every time I go away from that, I lose it. All right, so look what we got. We got just this red line down here. Now, we probably need to set our window. So let's go to your window, and let's do our time. We said our time was from about negative, or our window. Let's see. Go ahead. Let's do our window from, I don't know where it was. Let's go like negative 15 to 15 maybe, or no, let's make it 25. Keep changing. And the y. Now, what would our y be here? As long as we can see the x-axis, right? So negative 2 to 5 would be fine, as long as we can see the x-axis, because y is always 0 here, right? So we hit OK, and then go into your tab in here, and arrow up, and let's change our time here. We were like negative 5 to I don't know, 5 would probably be okay. Go negative 5 to 5. So we were talking about 5 hours before noon was kind of our starting point. 5 hours after noon is kind of what we're looking at. So if we look at this, okay, now trace and type in, where do we start? Negative 4. Type in negative 4. Might be off the screen there. There it is. Remember we said it was to the left, right? Now hit your right arrow. Hit your right arrow. Now, we said it was going to the right. Remember that? So keep going. So it was going to the right for a while. It was going to the right. Still going to the right. Now, you notice it's slowing down? You can see it, right? Because it's not making as big a jumps. It's going to the right, going to the right. Keep going. Okay, keep going. Can you just hold it down? Hold it. Does that work? Yeah. And remember we said it went to the right, and at negative 1, it stopped, we'd said, and then it's turning around. Now it's going back to the left. It was going to the left to what, about 3? Wasn't that right? Now it seems to be going pretty slow. He's just holding that down, so it's kind of constant time. So it's going pretty slow. Now it stopped right there at 3. Do you see that? And now it's going back to the right. Okay. So that actually shows where it is at those certain times. And there's the coordinates. Ooh, holy cow. Really jumped. All right. Okay, so hopefully I don't lose it. All right, so that's the actual motion of what's happening. All right, now, on that problem, when we did x prime of t, which would be what? T squared minus 2t minus 3. Remember that? And what did we say at t equals 3? We got a slope that was 0 at t equals 3. What if I wanted to know how fast that particle was moving at 1? How fast is that particle moving at 1? Let's pretend we were back in the one-dimensional motion equation. So we just had this equation right here. How fast is it moving? Well, that'd be the slope, right? That would be the slope right here. So we would do the derivative and we'd plug in a 1, right? So you go ahead and you plug in a 1 here. And what do we get? We get 1 minus 2 is negative 1 minus 3, negative 4. So we get x prime equals negative 4. Now, does that look like that would be the speed of the particle right there? It was going back to the left, so that'd be negative. And 4 looks like it's about the slope. That looks reasonable. So the speed was the slope. The speed was the slope. Okay, now let's pretend that it's a parametric equation. And we want to know the speed. We had a whole new equation for speed, didn't we? What was it? X prime squared, y prime squared. So let's do it for this problem. So what was x prime? We just did it. X prime was -4, and then that was squared. Plus, what's y prime for this particle? That's its vertical velocity. It's not even moving vertical. So it has no vertical velocity, so that's 0. So this would be square root of 16, which would be 4. Now, why didn't we get -4? Speed is always positive, right? Speed, so we're talking about on the path, what's its speed? So we're not talking direction here. We're talking just speed. We got 4, same thing. But that's different than slope, right? What's the slope of this path? As a parametric equation, what's the slope of this path? 0, right? That's not the same as the speed because it's slope of the path. This is not the path that the particle's on. The particle is just doing this. So see the difference there? Okay, that's why it's slope of the path. Now, what was our equation for slope of the path, by the way? Y prime divided by x prime. Well, at t equals 1, what's our y prime in this problem? 0. It's always 0. What's our x prime? It doesn't matter. It was -4. And 0 divided by -4 is 0. So the slope of the path is 0, but the speed was 4. Okay? So that's why it's different on parametric equations versus our regular functions that we have, speed and slope, because it's slope of the path. Okay, so we go back to our picture here. All right, go ahead and turn this one off and go back to the adamant one, Zach. And while he's doing that, I want us to think about this just for a second. I want us to think about this idea of speed and slope.
Happy day.
Did you guys want something? What? Oh, well, thanks. Yeah, there they are. Now they're looking at you.
You are tired.
All right, and now, yeah, go back and reset your window. It was like -5 to 5, I think. Oh yeah, turn that one off. Good idea. Okay, well you're looking at that. All right, now, so here's the path, here's the trail that Adam Ant is walking along, okay? Now, I want to jump ahead to question, let's see, on the worksheet here. So hopefully everybody was okay with question 2 where it said find dy dt and dx dt, just do the derivative of those, right? So x prime and y prime, that's your horizontal, this is your horizontal velocity, okay? And this is your vertical velocity. Again, going in those 2 directions. Speed, of course, would have its own equation. Slope would have its own equation. All right, then you're supposed to find the slope of the path at 6. What'd you get for that? Like 3 something? You just divide. You took y prime. You took your answers in 2. You took y prime divided by x prime. There's like 3 something. And then it said, is that reasonable? Well, where were we at on 6? Was right about here? Right when he traced it earlier at 6? Does that look like about 3.5? Yeah. That looks like about a slope of about 3.5. So that's reasonable. That's the slope of the path. Not speed. It doesn't have anything to do with speed. It's just the slope of the path. Okay, now, then we get to, then we said to skip number 4. Then it says he goes to the northeast for a while. When does he kind of start coming back? It's around 0.9 if you zoomed in enough. Okay? Then it says to reset the t-step to 0.01. So let's go ahead and go, let's do that. Let's zoom way in there. And let's reset your t-step to 0.01. And then let's zoom way in right at the tip here when he goes kind of northeast here at the beginning and then he comes back down. So let's zoom way in on that. Okay, zoom box is a good way to narrow it down a little bit. Zoom in the other class. Hey, Brett, see that? So that's, and now, yeah, then box it in again. Or, okay, yeah, a little more. I think would be good. Did you put 0.01?
Yeah. I'm pretty sure.
Okay,
I'll check it.
I thought you did. Yeah, no, I thought you did. It's kind of jagged.
That's weird.
Maybe that's all it can do. Maybe try it again and see. Yeah, just yeah, yeah, and that's probably on the T. I tell you what, I know what we can do. Go to the T step. I think there's a certain number of points it can do based on your T range. So let's change the T step. Go up to the, no, not the T step. You go up to your other graph. There you go. Yeah, change the T to 0.5 to 1.5 because we only really need to look at it right in that around 0.9, right as it's turning around. So if we go 0.5 to 1.5, then I think we can narrow that down a little bit. Now try 0.01. And I think it'll be a little better. Okay, because remember what it's doing. It's saying, okay, at this time you were here, and then at this time you were here, and then at this time you were here. It's connected, right? And so when you zoom in, if you're making too big of jumps in time, it's just going to be some jagged lines. So you need to narrow that down. So it's getting a little smoother here. Get a little smoother. So at some point, we can see. I mean, I would almost try. That's bugging me. Go back in there a little bit. Let's go like 0.002. I'm not even sure we'll be able to get me that. Oh, 0.002.
And T-step is the point between the C's.
T-step is, yeah, the T's that it's plotting. So you were here at 1 second, 2 seconds. That'd be a T-step of 1 if you were going every 1 second. Here we're going like every point of, that's not much different. But so anyway, so at some point it's traveling along. At some point it quits going down. The question in number 7 was, when does y stop increasing and start decreasing? What did you do there? Set y prime equal to 0. Absolutely correct. So, and I hope that was exactly what you thought to do. Because the question is just about y. Now, did anybody do the slope equation and set it equal to 0? Because a bunch of people in the other class did that. Now, it turns out it works. And I want to talk about that in a minute. But since they're only asked about y, and again, this is chart stuff, right? When y is increasing, y prime's positive. When y is decreasing, y prime's negative. So when y isn't doing either of those, y prime has to be 0. Okay? So you take this equation and you set it equal to 0. Now, that brings along its own difficulties. Go ahead and go to your scratch pad, go to your calculator part. And, okay, he's already got it here. Okay? Is that the equation? Is that the y equation? And he got that whole big mess with n3 pi's and stuff. Why? We need to limit it. And see, and I had a lot of people ask me about this. Well, what do I do here? Now, we've had this before, but we haven't had it for a while. So then we forget about it, right? When you solve a cosine or a sine, there's infinite solutions. You need to get the vertical bar in there. So go ahead and, now he changed that to an x. That's really our t, but that's fine. You can do it here. It doesn't matter. But we want our t to be between what? Yeah, about 0.5 and 1.5. We're looking for that first time it turns around and stops going up, starts going down. So let's do a vertical bar, and let's have it'd be x here in your equation, be between 0.5 and 1.5. Oops, that is that. And when we do that, then we get the 0.823 that we're looking for. And that is the point, and now go back to your graph. And so that is the point and trace at 0.823. Type in 0.823. Okay, and there it is, and that seems reasonable. Now, isn't the slope also 0 there, though? Right? And so some people in the other class did the slope, but think about what slope is. When is that going to equal 0? When the top is 0, which is when y prime is 0, right? The only time you really get in trouble is if y prime and x prime are both 0, right? Then you'd be divided by 0, but then that's something we got to talk about here in a second. So if you did the slope equation, you could do that. But again, that would be confusing speed, I think, with slope a little bit. But when its y position is not changing anymore, would be when the slope is 0. All right, now, what's the next question? Is he stopped at that time? Was he stopped right there? No. Why not? Because he's still moving sideways. It's kind of like this. When we talk about moving on the x-axis, we talk about, well, before you turn around, you have to stop. If I'm going this way, if I'm going to turn around and go back, I got to stop, right? Yes. But think about yourself driving in a car. If you turn around, do you stop? A lot of times, you do a U-turn, right? You never really stop. Well, but that's two-dimensional motion now, right? You're not just going east-west, right? If you're going to turn around, you'd have to, I guess, back up. You have to stop and then back up, right? You would have to stop before you do that. But you know what I'm saying? I mean, you literally, but we're doing two-dimensional motion. So we stop going vertically, but we're still going horizontal. But there comes a point where we stop going vertically, and that's this peak right here. Okay? So what'd you do? Did you plug in? What'd you do to show that or prove that?
Well, I just looked at the graph and said,
Okay.
obviously, the
Yep.
x has reached the maximum. That
There should be a way, though, that we could tell it.
is the same number.
Numerically, yeah. Put in that 0.823 into x prime, right? What you would want to do is you would want to take that 0.823 number and you would want to plug that in to x prime. Because that'll tell you its horizontal velocity. And it's only stopped if what? They're both 0. If x prime and y prime are both 0, then the thing is stopped. Okay, this is two-dimensional motion, both a vertical and a horizontal component. All right, now, one last thing on the Adam ant. And go ahead and reset your window back to its original window there. And your T and everything back to the original. And I want to volunteer to come up here and put a small circle at all the times when Adam ant has stopped moving vertically. Here's the mark. Take your time because it's going to take Zach a minute to. Bingo. Okay, here you go. Come on. Just one person. Not everybody at once. Come on, Steve. All right, put a small circle at every place where Adam has stopped moving vertically.
And I don't know. how it goes past
Well, that's
that.
kind of where it started, I think.
So we, yeah.
Okay. See, now, isn't it true at every one of those that the slope is 0? So those are kind of those traditional places we've talked about. That's where y prime would be 0. It stopped moving vertically, so there is no vertical velocity, right? But since slope is the equation y prime over x prime, I know the person watching at home isn't getting to see where he circled those. But anyway, so at those peaks, that's where y prime is 0. It's also where the slope is 0 because that's where that be. Okay, now, somebody come up and put an X. I won't even finish the sentence. We'll see if Tim was reading my mind. It's kind of hard on this one. I drew an easier one for the other class. That's probably it. Okay, what was he marking? When he quit moving horizontally. Those are the places he quit moving horizontally. What's the slope at those points? Right? It's vertical. Those are all the places you would have a vertical tangent. Well, look at the slope equation. That's when x prime is 0. When he stops moving horizontally is when x prime is 0. And those would be vertical tangents. So on a parametric graph, points of interest would be horizontal tangents, where the horizontal velocity is 0, that's when y prime is 0, and when x prime is 0 is when it quits moving horizontally, but it might be moving vertically. Yes?
So if you were completely stopped, would those two overlap?
That's a really good question, because remember, if you're completely stopped, you get 0 over 0. Now, does that really mean a vertical tangent? No. What's a vertical tangent or a vertical asymptote? What kind of situation is that? That's like a number over 0, right? We just had to do that with limits, like 2 over 0, 3 over 0. So a vertical tangent is going to be when it is moving vertically, but it's not moving horizontally. And a horizontal tangent is when it's one or the other. But a 0 over 0 situation, it could be stopped a lot of different places in there, right? Where the slope would be different things, but so you wouldn't be able to tell from the slope, in other words, yes.
Isn't like the only time it can be 0 over 0 is when it reaches a sharp point, which is the slope there is undefined anyway. Because like if you're curving back, you're going to be moving.
You're always going to be moving. It'd have to be a point where you didn't have any motion in either direction, right?
0 to 0 kind of makes sense in that situation.
Yeah, so it would be kind of like I thought that might be happening here, where it's literally a sharp point where it's going to come and immediately change direction. And there's probably not a real easy equation to write where that would happen. You know what I mean? Except for linear kind of things, linear pieces. But yes, I think that's exactly what happens. As long as it's a curve, it's going to be moving in one direction or the other. And so you're not ever going to get them both being 0. Because, how could you have both a horizontal and a vertical slope at the same time, right? And so what you have is some sort of sharp point kind of situation. All right, so I wanted to make that connection with the speed, the slope, and this horizontal vertical velocity. I think that's really important. But as we go forward with parametrics, on the test, on the quiz that we have, I'll kind of show you. I want to kind of focus in on the book here a little bit and show you kind of the things I want you to be able to do. Now, obviously, one of them is just be able to know any of these formulas. Understand that x prime and y prime is horizontal vertical velocity. The slope of the path, y prime over x prime. Okay, but that's the slope of the path, not where the particle is at any time. That's just slope of the path. And then speed of the particle on there. Okay, is that equation there. And be able to just use and know those equations. All right, so that's very important. And we're going to get into a few of those here today. All right, let's, okay, here's the next thing. So get your notes out. And so the next thing we want to talk about is just kind of just for a little bit here, some non-motion parametric type equations. Now we can always, when we're doing a parametric equation, think of it as a path and think of it as a particle on the path at a certain t value. Like we did the unit circle yesterday, it wouldn't have to be motion, but usually it makes sense that when t is 1, you're here, when t is 2, you're here. So it just always makes sense to think of an object moving along a path, I think. All right, so go ahead and go to your calculators, and I want you to put this first one in. Now, Adam, Matt, we're probably done with that. You could probably clear the scratch pad if you want to now. It's up to you, or you just turn them off. But, Zach, let's go ahead and let's graph this this equation. Everybody else can if they want. Just this first one here. Okay, the one on the left. X equals t and y equals t squared. Okay. Now here's what he's got. You guys can see what you think. What do we got there? What do you think that is? Think it looks kind of like half a parabola. It could be exponential. It's got that look to it. But when I see this t squared, maybe parabola. Really, would it be that easy? That it's that and it's got parabola. Why only half? Our t's started at 0, right? I mean, for example, so let's go back into that equation. Let's talk about changing our t values and maybe our window a little bit. Well, you got to arrow up to the right equation. Okay, now let's talk about this a second, because one of the things you're going to have to do in your homework is they're going to say, hey, what is the location or what's the point on the graph at t equals 0? So what would you do? Just forget you had the graph staring in your face. You just had this equation, and I said, hey, what's the location at t equals 0? What would you do? Put 0 into both of them, right? Why in both of them? Because 0 here gives you the x, 0 here gives you the y. That's its coordinate, right? When we talk about where is the particle, we're talking about its coordinates, right? 0, 0. So at 0, this particle is at 0, 0. Where is it at 1? When t equals 1. It's at the point 1, 1. How about at t equals 2? 2, 4, and so forth, right? So this equation gives us its location at certain time values. All right. Now, since we started with t equals 0, we didn't get any negative, right? So let's go negative. Negative 5 to 5, let's say. Let's just go negative 5 to 5, okay? And you can leave the t step there, that's fine. So what's kind of cool about this with parametrics, we can graph a basic parabola. I mean, this looks like just the plain old y equals x squared parabola, right? Think about the points we just said, 0, 0, 1, 1, 2, 4. That it looks like it's just plain old y equals x squared, right? But we were able to graph just a piece of it by just changing the t range there, right? Okay, so trace here real quick. Trace, and let's just double check ourselves and make sure we were on the right track there. So if we type in a 0, we're at 0, 0. Type in a 1. We're at 1, 1. Type in a 2. We're at 2, 4. Yeah, okay. Piece of cake. Now, if we think about this a minute, does it surprise you that this equation, or that this came out to be that? I mean, look at this. Does it make sense that it was that? Anybody see something there that mathematically you could do? Isn't it just a simple substitution, right? If x is equal to t, doesn't that mean I can substitute x for t? So I can just, if x is equal to t, that means I can just come down here and where that t is, put an x. That's called eliminating the parameter, eliminating the t. That's something you're going to maybe do on the quiz. You're definitely going to do some of it in the homework. Now that's about as easy as it gets right there, if x equals t, right? You just substitute, you put it in, okay? But now let's go to this one, okay? Now let's, Zach, go ahead and graph this one. So now I want you to graph it on top of this one. So I want you to leave x1, so you guys can do it on yours if you want. But let's go to x2, and let's put in this other one. So we want to put t cubed and t to the 6th, and graph it. What do you get? Oh yeah, it's got to turn out, yeah. what happens? It's the same exact. Remember how we were talking a minute ago about how you could have the same path, but two different objects on the path? Right? Well, that's what we have here. We have the same path, but two different objects on the path that would be there at different times. So, now, why is it the same path? Do you see how this could also equal y equals x squared? Why? Because if you square, I mean, there'd be several ways you could do it. One way of thinking would be solve this for t. Sometimes that's the best way to think about it. Solve this for t. Well, you cube root both sides, which would be a cube root is what, 1/3 power? So if you cube root both sides, you'd have that, and then substitute it in. So you'd have y equals x to the 1/3 to the 6th. Power on a power, you multiply. 1/3 times 6 is, sure enough, it simplifies that. Now, probably don't have to go that much work. You can probably just say, hey, t cubed, t to the 6 is just t cubed squared, right? And so that'd be t cubed is x, so substitute x squared. Okay, either way you do that, you get this. Same exact path, but they are different objects because let's trace. We just got done tracing on the blue one. Now let's trace on the red one. So go ahead and trace on the red one and type in a 0. And so at times, type in a 0. Oh, we're on the blue one. Hit your up arrow so you get to the red one. Okay, now trace at 0. So they're both at the same place at the beginning. Kind of like if Mandy and I were racing, right? We'd be at the same place at the beginning. Then type in a 1. And then we're still together at 1. But then type in a 2. See, and she's...
Those are 2 steps.
2 steps, yeah, 2 seconds, right? And so she's back there at 2:04, and I'm up here at 8:64, right? I went way past. Okay? And then I'm laying by the side of the path. And then I'm laying by the side. Yeah, those will be 2 seconds, and then I'm laying by the side of the path till I remember. All right, so 8. So there are totally different places on the path, but it's the same path. Same path, okay? But 2 different objects. So that's kind of interesting. Here's another thing you can get with these parametric equations. You probably can already tell what that's going to be. What's that graph going to be, this first one left? Isn't that just going to be the basic sine graph? Because x equals t, so we can just do an easy substitution. We can put an x in for t. So this is y equals sine x. So this graph right here, the path at least, is going to be y equals sine x. Now remember, when we take out the t, what we're doing is eliminating knowing where the object is, because we're taking out the time element. All we're doing when we do this is giving ourselves a graph of the path. Just like on the last one, both of them we took out t, both of them had y equals x squared as the graph of the path. The t is what told us where the particle was. So this is just going to be a basic sine graph. Zach, go ahead and put it in. Take out those other ones you had. Being a presenter is tough today. A lot of work. So this should be the basic sine graph, but again, we could just do a piece of it because we can just tell which t values we want. So if we go back to this, okay, and you can leave that -5 and 5 and all that. That'd be fine. And then let's move your window. Just do a standard window. Just do a zoom standard real quick. Okay, and so we just did from -5 to 5. T and x are the same, and so our x and our t are the same, and so that's a piece of the sine graph from there. All right, now, okay, so no big deal. So hopefully what that tells you is you could use parametric equations to graph any simple equation you wanted, right? If you wanted to graph e to the x, what would you do in parametric to graph e to the x? X equals what? T. Y equals e to the t, right? That would give you the graph of y equals e to the x. Okay? Now, what did I just do right there? So I interchanged the x and the y. That sound familiar at all? Interchange the x and the y. When do we interchange the x and the y? think I've heard of that. Maybe I haven't. Inverse function. Remember inverse functions? You interchange the x and the y. Look how easy it is with parametric equations. In parametric equations, we have a separate equation for the x and the y. So to interchange the x and the y, we just interchange our two equations. What's the inverse of sine? No, that's reciprocal. What's the inverse of sine? Arc sine. The arc sine, or the mirror image graph, right? So let's interchange that. Zach, let's do it. Let's make that a separate graph. Leave the sine graph up there. Go into your x. Okay? Look at the red one. It's the mirror image. It's the inverse trig. So you can't do that because that's not a function, right? In function mode, you couldn't do that. Now, you could go to arc sine, and it would just limit. It would just take a piece of it so it would pass a vertical line test. But that's kind of cool. That's a real easy way. Parametric equation is a real easy way to graph inverse functions. Think about what the original function would be, x equals t, y equals whatever, and then you want the inverse. What would be a cool way to graph ln x? I'm sorry, I could do this all day long. What would be a really cool way to graph ln x? Well, what's the inverse of ln x? No, what's the inverse of ln x? E to the x, right? Natural log and e to the x are inverses of each other. So we just said this would be e to the x, right? So what's its inverse? Yeah, but I mean, with parametrics, to get the inverse, we interchange the x and the y. So go ahead and do that. Let's interchange the x and the y. So let's let that should be e to the t. Now, wait, what did he just grab? What's the black one? Find out. Just stop where you're at. That's e to the x, because what did he do? He took the ln function and switched their x and y by switching the x and the y here, right? So he switched that, so he got the inverse of ln, which is e to the x. If he changes this ln t to e to the t, then he'd be doing the inverse of the e to the x graph, which should be the natural log graph. Okay, e to the t, there's a natural log graph. Okay? Good stuff. All right, so what's next? We got one more cool problem to do. All right, here we go. Last thing, you want to write this down in notes because you got a homework problem that's like this. So in your homework, you're going to have some work with parametric equations. One of the things they're going to have you do is eliminate the t. They're going to have you solve one equation for t and substitute it in. There's going to be some problems about maybe speed or velocity or some of that a little bit. Not as much. That was our focus more yesterday. And then there's going to be a couple of storage problems like the one we're about to do right here. Okay? Now, and it's going to have to do with the speed equations and that stuff as well. So what we have is a pitcher, if you can't tell, on the mound, throwing a baseball. Here's home plate, 60 feet, 6 inches away, which is 60.5 feet away. Okay? He's going to throw this ball from an initial height of 7 feet, okay, when it leaves his hand. When it leaves his hand, don't worry if you can't draw your picture as good as I do. When it leaves his hand, he's gonna be throwing it horizontal when it leaves his hand. Okay? Now the ball's gonna drop because of gravity, and we're gonna ignore air resistance, which of course would be really bad in baseball if you ignore air resistance and curved balls would be no, right? And so, but what's that mean if we ignore any air resistance? It's not going to slow down at all, right? The ball won't slow down at all. Matter of fact, the ball will actually speed up, won't it? Because it won't change horizontally, but it's going to be going down.
What do you have with it? Calculator?
Your calculator? Ooh. Anybody see a calculator back then? Were you carrying it around with you?
I have no idea.
I don't think so, no. I didn't. As a matter of fact, I'm missing one in here.
Alec. Yeah.
Probably.
It's probably.
What color was it? Oh, yeah. Wait.
Oh, he stole
There you go.
it.
I did see it.
Yeah.
All
All
right.
right.
I was. All right. All right. So, I didn't say surprise. I just said fun. All right. So, so if he throws this ball horizontally with an initial velocity of 150 feet per second, it's going to be going 150 feet per second horizontally the whole time because it won't slow down because of friction or air resistance. And gravity is going to be pulling it down. So, okay, so anyway, so that's all we know. We should be able, what we want to do is write a parametric equation of the path of this ball. Right? That's what parametric equations do. They give us the path of an object. So we should be able to do this. Now, first of all, what would be a better label from a calculus perspective than initial velocity here? X prime. Because this is the horizontal velocity. And I didn't even think you were paying attention back there. Good job. God. Sam's been bragging. Okay, the horizontal velocity is x prime, right? That's what we've been talking about. That was the first page of notes here, x prime. So we should call it that. All right, and what's the y? What's happening with the vertical? Just, you guys said it, gravity, right? And we're going to use feet, so it'd be negative 32. But what derivative is that?
Double.
That's double prime, because that's acceleration. So the two things we know that are acting on this movement of the ball is its horizontal velocity and its vertical acceleration. Those are the only two things we know. Now, you will not have to do this on the homework and you will not have to do this on the quiz, but I want to do it because we've done this a little bit before and I think we should be able to. But I won't require it. We should be able to find our x and our y equations from that information alone right there. How? How are we going to go from x prime to x? Antiderivative. That's basically a differential equation, isn't it? So what's the antiderivative of 150? Time out. What did you just say? You really want me to have a x here and then 150x here? T. Thank you. Our input variable is not x. It is t. Okay? 150t plus c. Now, what is the c? Well, thank you. Yes, c is a constant. Yes, very good. I did. Yes, I did. How much is c? It'd be the starting x, right? When t is 0, x would be c. So at time 0, the ball's right here. What's x?
60.5.
Well, you're right. We probably need to, let's call this point right here, let's make that the origin. So out here would be, x would be 60.5, and then that way up here is 7, right? Like that. So at the beginning, what's the coordinate of the ball? 0, 7. So what's its initial x? 0. So when t is 0, at time 0, x is 0. What's that make c? 0. So c is 0. So our x equation is 150t. Correct? Now, again, you will not have to come up with that on your own on the homework or on the quiz, but it'll be given to you. Okay, what about the y? Well, we know y double prime is this, so we could do the antiderivative to get y prime. What's that? T, very good. Plus c. Now, what's that c? It's funny your first time. All right. Starting vertical velocity, right? It's the starting y prime. In other words, when t is 0, c is the y prime. When you throw the ball first, what's y prime? It's the vertical velocity. Remember we said we're throwing it horizontally. So when we first throw it, it has no vertical velocity. So that would be 0. Okay, so good. So c is 0. So now we do the antiderivative again. No? Oop. T squared plus c. What's that c going to be? That's the starting y value, which is 7. So when t is 0, c is the y, the starting height, that's got to be 7. So our y equation is negative 16 t squared plus 7. So we could build those equations. So So what we have then is a parametric equation of the path of this ball. Now there's all kinds of questions we could ask. First question, when does it cross home plate? When does it cross home plate? How long does it take to get to home plate? What do we do?
Oh, C is 60. Yeah.
So right now we're using these two equations, right? So we take this equation, we want to know when its x coordinate is 60.5. So we simply go 60.5 equals 150 t. This is the part you are going to have to be able to do. You're going to have to be given an equation that represents horizontal and vertical position of some object and be able to use those equations in a proper way. So when's it cross home plate? When its x is 60.5. So we solve that and we get what? Once again, thank you very much. 0.403 seconds. So less than half a second, which makes sense. Less than half a second to get there. It's going 150 feet every second, plus gravity pulling it down, right? It's only going 60.5 feet. So about 0.4, so when does it cross home plate? At about 0.403 seconds. Okay? Is it a strike? Now we will have to, we won't be able to count whether it's inside or outside, because that would be a third dimension, right? What's that?
Like, I haven't ever figured that out.
That's right. I mean, you're right. And so we'd have to be given some sort of parameters what a strike is. But what is the question really asking? How high is it, which is what variable? So the question is really, what is y when t is 0.403, right? Because it crosses home plate when t is 0.403. So at that time, what's its y value? So we would be doing y equals negative 16.403 squared plus 7. So we would type that. Go ahead and do that. What do you get? 4.401, so about 4.5 feet. Now, is that a strike? Well, it depends. Steve's a little taller, 4.5 feet, probably a strike. 4.5 feet on me, be close, probably be getting up there a little bit, right? 4.5 feet. You know, this is probably about 3 feet. Or, you know, that might be a little, it might be a little high. For some people, this would be probably high. But you'd have to have some parameters. But the important thing is that you understand what equation, what to plug in and where, okay? When it crosses home plate, how fast is it going? How fast is the ball going when it crosses home plate? No, because it's falling. X prime is just 150. We already know that. This is the square root equation. This is the speed equation. We have a particle. We have an object on a path. It's got both horizontal and vertical movement. And so this is the speed equation. So we would want x prime squared, and x prime never changes. X prime is a constant, so that's 150 squared. And what would the y prime be? Y prime was negative 32t. But what's t? The 0.403. So we're going to have negative 32 times 0.403, and then all of that squared, and then the square root of that whole thing. So go ahead and do that. So 150 squared, that'd be the x prime squared, and then this would be the y prime squared, but we had to plug in the 0.403 because y prime is changing. As the ball's dropping, it's going a little faster all the time because gravity's pulling it down. Okay? $150.553 miles per hour, whatever, feet per second, I guess. And it's fast, and we said that the ball is actually, which is not realistic, the ball is actually getting faster. right? Because it's going to stay a constant 150 feet per second because of no air resistance. Plus, it's dropping, so it's picking up speed a little bit. So the fact we got a little bit higher number would be reasonable, okay, in this problem. All right. When would it hit the ground? When would the ball hit the ground? You would take the y equation and set that equal to 0. Right? Because y is its vertical position, its vertical height, so when it hits the ground, the y is 0. And so you put a 0 in for y and you'd solve it, and that would tell you when it would hit the ground. And then what speed was it there? Right? You take that time and put in the speed, right? So we get to use all those, and the only one we didn't use is slope, and I'm not sure why we'd want to know the slope of that path. It wouldn't be speed, remember, it's different. But what's the slope of the path? Well, it'd be fairly flat, right? Be a negative a little bit, aiming going down a bit. And that's the slope equation. So you need to be able to work with these. Now, you wouldn't have to come up with it, but if I gave you this, and you've got a couple problems in the homework where they give you that, and then you've got to work with it and solve those equations and use it. All right. So your homework, if you get out your homework assignment sheet here for chapter 4, take a look at those. Now, we are, I have kind of jumbled this around a little bit. So we're not following this right down the line quite, because the section we're in is 4.4 now. All right? So if you look at that assignment sheet, there's a quiz, the third quiz there, the one that says 4446, you can cross that out. Okay, the quiz 4446, because 46 is a section we won't do on a quiz until we get down to the take-home quiz. We'll do some stuff on that take-home quiz, and then we have a no calculator quiz. There might be some questions on that there, but so there won't be a quiz with 46. And then 4.4, we're going to move up to the quiz right above it. So the 4.3, 4.5 quiz will also have 4.4 in it. Okay, so the next quiz we take will be 4.3, 4.4, and 4.5. All right, so your homework is the 4.4 line, 4.4. And you can cross out number 11 and 12. Don't have to do 11 or 12. Okay? All right, so as you get started here, the first couple problems simply give you a parametric equation and ask you to graph them on your calculator, trace at a couple of points and write down what the points are, and then mark the direction of travel. That is something I will ask you to do on the next quiz. You will have to plot a parametric graph, probably give you the window to set and everything, and then if it was adamant, mark the direction of travel like with some little arrows on there or something like so. And plot some points. And so you might have this point right here, might be t equals 1, and it might be the 0.27 or whatever. So plot some points, mark the direction of travel, that kind of thing. When you get to number 6, that's where it wants you to write an equation in terms of x and y. That's the thing we did with the substitution, when we were substituting the t in and that kind of thing. So eliminating the t, and then it gets into the other ones in. Once you get going on that, you should be good. Okay? All right, you got the rest of the time to work on them.